and then we'll be all right. So thanks again for being here. I appreciate it. I know, we're still all doing what we can to do what we need to do and get through life here. I was lucky enough, I got to go hiking this weekend with my son and my wife and my mom, and my dad stayed home to go play golf or whatever, but whatever, he's almost 80, he can do whatever he wants. So we had a good time in the Eastern Sierras, and I'll maybe show you some stuff on Thursday if we have some time. But just a little bit of what we got planned coming up for today. Just a small geo news. We'll take a look at some felsic volcanoes. So last week we looked at the mafic volcanoes, the ones that were made of more dense lavas and made the lava flows and the lava tubes. The basalt basically is what all that was. We looked at A'a and Pahoehoe and all the different kind of flavors of basalt that are made. And then today we're going to be looking now at the felsic volcanoes. Well, we're going to take a look at on Thursday, probably. We're going to look at Yellowstone, and we're going to use some of the latest science and latest data and observation tools to figure out if are we all doomed? Is Yellowstone going to erupt? Every once in a while, it seems like once a year or so, somebody posts like a video of a buffalo running in Yellowstone, and they say, oh, it's evidence that Yellowstone's going to massively erupt and everybody's going to die. Hopefully after this class, you'll know that you don't need to pay attention to those folks. And we do have ways of monitoring those volcanoes. All right. So same thing, more voices, rich experience, all that good stuff. I will just say last week, one of the things, I think it was last Tuesday when we first started doing some of the looking at the different igneous rocks, a few folks felt a little left out. So let's just make sure we're doing our best to incorporate and include folks in the activities and asking questions of one another. And that's kind of where we'll head. All righty. Whoops, sorry. I was making my face big on my Zoom anyways. So only a couple things you need to geo knows today. And the first one is the Cumbre Vieja volcano is still erupting decently in that Canary Islands that we looked at last week. So if you want to search that up, you totally can. But the other thing I want to mention here is just, I showed you at the beginning of the month about the mineral cup. And now we are down to this fight today between serpentine and zircon. So remember, zircons are the minerals that we use that generally trap a lot of the radioactive elements that we can date. And they're the oldest, they're some of the oldest minerals on Earth. Like some of the zircons are like 4.4 billion years old. So there's some of the oldest traces of continents and things that are left on our continents here. But it's going up against the California state rock, or the minerals that make up the California state rock, which is serpentine. Voting ends in like 3 hours for this. It's like a 50-50 tie. So if you want later on, oops, I gotta let somebody in. If you want later on here, I'll copy this link, and we got a poll for California. So if you want to go Twitter vote in the mineral cup for serpentine, or if you want to vote for zircon, you can vote for zircon too. But serpentine's really cool. And if you search the hashtag serpentine, you'll see all sorts of really pretty geologists, or not pretty geologists, but geologists posting their pretty pictures of serpentine all over Twitter and talking about vote for serpentine. And really the zircon crew, I don't know, they're pretty into zircon, so maybe an unhealthy amount. So we need to vote for serpentine to make sure zircon doesn't get into the finals. All right, so it's pretty cool. And if you get a chance, you can do that. The other thing I just want to mention, and we'll look at on Thursday, the final rain totals. Thursday is the end of our water year in California. It starts October 1st and ends September 30th. So we'll take a look and check in at how bad the rain is. The clouds this morning were amazing and great, and it's only supposed to be about 78 degrees, but that could be bad for fire weather coming up in the next few days. And you'll notice it's going to get a lot warmer right around the weekend, back into the 90s. So usually with that, we'll have changing winds that could increase smoke and fire and things like that. So just be aware, and we'll look at that in more detail a bit later on. All right, on Thursday. So for today, This looks very similar. This sketch note looks very similar to what we did last week with the mafic volcanoes or the basaltic volcanoes. But this week, it's all about the 3 felsic types of volcanoes, the stuff made of granitic magma. So if this lava were to cool underground, it would make big crystals and cool into granite, the coarse grain stuff. But instead, it erupts out and generally makes more explosive volcanoes. All right. So some of the things we're going to look at the 3 different types. You can have a little info on it. You'll have some California examples in your pocket in just a few minutes because you guys are going to go on a little virtual tour here. And then for the volcanic hazards posed by the felsic volcanoes, for these, you just got to give me some sketches and descriptions. And I kind of gave you some ideas of what some of the different hazards look like, and I'll be showing you like little video clips and letting you see in person what these all mean, and they're not just words. So you can put some of those down on there to help explain some of those different hazards, which is pretty awesome. You'll see. And then I think we're going to get to some of this today, talking about California volcano risk, which is kind of looking at, based on everything we learned today and last week, what California volcanic risk should the state be most concerned about in your opinion? So, and why? So you're going to use some of the evidence that we're learning today. Don't just say it's like, oh, I think, you know, it's this risk, and don't go into any more detail. Give me some risk, give me a little sketch about it too. Sorry, package, I guess. I don't know if anybody else has that when your train of thought gets broken. It takes a second to reset. That's me. But you want to support your claims with evidence about those volcanoes. All right. So in the volcanic risk. So what should the state be most worried about? I'm going to be showing you 5 or 6 different slides and pages of data and things to look at and for you to interpret. And there's no right or wrong answer here as long as you support your ideas with evidence. And, you know, I mean, should any of you become teachers or even like local politicians, state politicians, something like that someday, this is something to have in your back pocket to think about as we like make expenditures going into the future. Okay, so that's kind of what we're looking at there. And, you know, what level of concern should we have about that risk? That's the other thing. So what do you think is the biggest risk? What level of concern should we have about it? Is it like keep you up at night concern or just a general awareness? Should we all be freaking out? Don't ever, that's always never the right answer, but you know, just that's what we're going to be looking at. And then on Thursday, we'll get into Yellowstone and figure out if it's going to blow up and affect us. So last week, this is what we looked at here. We looked at this fissure flows, cinder cones, and shield volcanoes. All of these had in common that they were mafic volcanoes. Cinder cones, remember, were kind of short and squatty. Shield volcanoes were massive. You got to look at some of the photospheres of the lava tubes and lava beds out in Northern California. And now today we're going to look at the other volcano types that are more explosive. They're generally a little bit larger and can go boom. And sometimes they go boom, sometimes they squeeze out, and they make these different volcanoes right here called a composite volcano, caldera, and a plug dome. And so these are kind of the 3 that we're going to be looking at today. All righty. So the reason I'm showing you this Bowen's reaction series again, what this just shows, if you remember, the minerals up here on the top are the minerals that crystallize first and kind of melt last. And when we look at the mafic rocks in cinder cones and shield volcanoes and fissure flows, they're generally made up of these mafic minerals, which means they're coming from a hotter part down underneath the Earth's, in the Earth's crust. It's a hotter melt. And so this is the type of mineral that's found in there. The felsic things we're going to be looking at today, these are the result of those subducting plates. So when you have the subduction zone and those ocean plates start subducting and going underneath the ground and they start melting a little bit, partially melting, the first elements and the first minerals that start melting out of that are things that will make potassium feldspar, muscovite, mica, and quartz, which if you put all these together, these are the granites, right? So these are the things that start melting first. They bubble up to the surface and then eventually make magma reservoirs, which can erupt and create the more sticky explosive volcanoes. And so just to reiterate, remember we had Mount Lassen right up here, it erupted. I showed you the video last week, so we'll kind of skip this part, but 1915, 1916, 1917, I think is when Mount Lassen erupted a few different times. So within the last, just a little over the last 100 years, we've had historical eruptions in California, and it's something we need to know about there. And if you do get a chance to go to, Mount Lassen, this is some of the cool fumaroles and mud pots and things that you can see up there. And I should mention, we're only talking about kind of 3 major types of volcanoes, but there are also mud volcanoes in the world where it's basically hot water and dissolved clay, or not dissolved clay, but suspended clay, make these big bubbling mud pots that can erupt mud, which is pretty awesome. So before we get anywhere else, here's what we're going to do. We are going to go on a quick little virtual tour in your group. So here's a Google Earth link. And when you open the Google Earth link, it should take you to this page right here. Get rid of that. Oops, let me see here. Give it a second. All right. And you might recognize it a little bit from some of the other volcano things we've looked at earlier this year, but basically, oh my gosh, it's taking road work out there. What you're noticing here is it's 10,000 years of volcanoes, if you can see that right there. We looked at this when we looked at the patterns of plate tectonics, but what I'd like y'all to do is just kind of zoom in and fly in, and what we're going to care about is some of these California volcanoes. And the way we're going to care about those is, let me give you this link here. Yeah, here it is. All right. I think this should open this link. There you go. Yeah. So it's just a pretty easy diagram. And all you're going to need to do, and I think everybody can edit this. Let me see. Yep. Okay. So you're going to be getting into your groups, and you're just going to go down and basically find the different volcanoes that are in here, kind of type in its name and tell us about what the volcano is made out of. So let me show you the quick way to know if it's in California or not. If you go up to the top left-hand side of Google Earth, you'll see there's like a little hamburger thing where the menu is. If you click on that, go down to where it says map style. And then if you click map style, if you click exploration, this big tab right here, it'll turn on borders and labels and places and things like that. That way, when you zoom in, you can kind of see the dotted line of California right there. So all I'm looking for is for you guys to just kind of go around, find the different volcanoes in California. You can click on it. And when you click on it, it tells you what it is, where it is, and then just gives you a small little description about what these things are. If you want, you can click the little paper airplane and it flies you in right into there so you can see what's going on. So the Salton Buttes are right down there at the end of the Salton Sea. There's also some really awesome mud volcanoes in there that maybe I'll show you some pictures of on Thursday. But remember, you can zoom in, you can use shift and use your keys to look around and all that other kind of cool stuff. And then when you're done, you can ignore the return to start down there. Just hit the X button and that closes. And then you can zoom out and then just go flying along the rest of California here and find a few of the other different volcanoes in California. Click on it and it'll tell you a little bit about it. All right, so we're going to spend about 15 minutes or so here exploring these different California volcanoes, seeing what you see. And then this way, as we start going through forward and talking about some of the other volcanoes, you're like, oh, I know where some of these are. I know where I can find some of these in California. All right, so all you got to do is just when you get into groups, you just got to fill it in into here like this. So just give me the name, the type, general location, and that's what we're looking for here. Okay. So I'm going to put you in breakout rooms. My suggestion, right? Maybe have one person share the screens and have another person recording, things like that. That generally works pretty good. Let's see here. So we're gonna have 6 breakout rooms, 3 people a piece. Say hi to everybody. We'll make this going for, let's see here. Let's say 12 or 13 minutes here. We'll do 13 minutes and we'll see how that goes. All right, just to get familiar with us and see what's happening all there. So here you go. See you later. Hi, Jennifer. Were you in room one, Jennifer?
Yes, and then it kicked me out, so I had to come back
Yeah,
in.
no problem. No problem. I'll put you back.
Thank you.
All righty, welcome back. So good job. You guys a lot of groups flew through. Some of the groups I know were looking at things a little bit more, well, not more closely, but took the time to fly around some other things and saw some stuff, which was great and cool. But hopefully you noticed like shield volcanoes and cinder cones and stratovolcanoes and plug domes. Maybe you heard that as well. Were there any terms that you saw that were like, huh, what the heck is that? No? All right. I know some folks, well, I mean, if you did down like UB craters out in Death Valley. Oh, pyroclastic, that's a great one. Pyroclastic is something we're going to see in just a few minutes. That means pyro means fire and clastic means broken bits of rock. So pyroclastic flows are basically exploded bits of a volcano that come out and run down the hill very quickly and very hot. All right. So yeah, that's what pyroclastic is, and we'll see that in just a minute. And then the other one we're going to take a look at is just really fast. I want to show you there's a thing called a MAR, M-A-A-R. And basically what happens here is when magma gets its way very close to the surface and interacts with groundwater, that magma causes that groundwater to flash to steam really, really fast, which basically causes a massive steam explosion with some of the magma that's in there as well, and can blow big holes in the ground. And that's what happened here at Ubehebe Crater in Death Valley, which is pretty awesome because all the layers of rock that you see on the canyon wall here, these are all sedimentary rocks. And then the blacker stuff on the top, this is from the basaltic magma and lava when it interacted with the steam, created these little ash flows and little small pyroclastic flows and things like that coming out of there. And it's a cool little place to get a chance to go see, but that's less than a couple hundred years old probably. So just something to think about. It's kind of really debated still exactly how old this one is, but it's pretty fresh and pretty new and a pretty cool place to go see. All right, so I highly recommend Death Valley if you get a chance when it's nice and cool. So yeah, we saw Lavic Lake and Crater Lake and Shasta and Ubehebe craters. I mean, we got all of it in California, and so many people don't even realize it. And I told you there was mud volcanoes, and so I went and found them really fast. But these are the mud volcanoes down at the end of the Salton Sea, right near the California-Mexico border down there. And it's really awesome. I mean, they're just these little cones, and they bubble out the mud, and it looks like it has its own little muddy pahoehoe flows coming out right there like that. And I just like going there and watching it because the mud as it comes out, it's really hot. Even it's not something you want to touch or anything, but it just makes these big bubbles and whoop and pops and then runs out and flows out. It's a pretty cool thing to be able to get to watch it. So you can go see that. And also, I don't know if you guys noticed, but that Clear Lake volcanic field too over in Clear Lake volcano up here over by Clear Lake in Sonoma County and stuff, Napa County, that has the world's largest geothermal electricity producing area. So it's tapping into the magma chamber that's underneath Clear Lake there. And they pump water down into the rocks, and it gets hot because there's a magma chamber nearby, and then they bring that warm water up or hot water up and use that steam to turn turbines to create electricity. And if you live in Turlock, Turlock Irrigation District, their electricity, our company here, we get, I think, about 1.5 or 2% of all the electricity we use in Turlock comes from parts of things that we own over there in the Clear Lake volcanic field, which is kind of cool. All righty, so I just want to show you this really fast. I gotta give me a quick second. I gotta shrink my face so you can see things on the map here. On the left-hand side, this is kind of an overall chart of all the different types of hazards that volcanoes, especially these felsic or stickier volcanoes, more explosive volcanoes can produce. All right. And so when somebody was asking about pyroclastic flows earlier, this is kind of what they look like right here, or when the ash kind of barrels down the mountain coming down that way like that. Those are both examples of pyroclastic flows, hot, steaming ash over 1,000 degrees. Remember, the ash is broken rocks broken fragments of lava, lava that doesn't flow like you see in Hawaii, but it's still lava. It's just very sticky. And so fragments of that coming down, it's not a pleasant thing to have to experience, I would not imagine, right? We're going to learn about these things. We know what lava flows look like from last week. We're going to talk about these things called lahars, which are mud flows. We also have landslides. We're going to see Mount St. Helens had a complete landslide, which uncorked a huge eruption. And those are kind of the big things, well, not to mention like ballistics or things that are flying through the air. That's pretty bad. And then another one that we're going to take a look at is what we call tephra and ashfall, which is basically if you launch those fine particles high enough into the atmosphere, eventually it's going to get caught in the wind and blow downwind and eventually settle down to the ground somewhere else. And, you know, even powdered rock is still pretty dense and it can mess up engines and things like that. So it can be a pretty major hazard as well. So on the right hand side, and we'll get into these, I just wanted to kind of give you an overview to put in the back of your mind here. On the right hand side, these are the California volcanoes that we kind of closely watch in California that might be somewhat of a threat. All right, so if you see red, the red triangles mean we think this has potential to be a very high or high threat to population centers in California, right? So maybe not necessarily like a global cataclysmic thing, but to people living nearby, it could be a pretty high threat, could really mess some things up, right? If you see kind of the like Long Valley where it says high to moderate, there's a reason there's both there, because there's some cinder cones there that would be kind of just moderate threats, but there are also some stickier, more explosive volcanoes that could potentially be a threat to California someday if it erupted again. And then the yellow ones are kind of moderate. And then also here's the Salton Buttes down there. And the last thing is if you see the little star burst behind it, that means it's had an eruption within the last 3,000 years, which geologically speaking is like just a blink in the eye, right? So that 3,000 years ago is what we would consider very recent. In terms of geologically speaking. So this is what we're looking at here. Last week, we looked at those different textures of the rocks. So now we're going to be looking at this glassy stuff, the vesicular stuff, some of these pyroclastic flows coming out of the volcanoes, out of these magma reservoirs / magma chambers here. And I don't know why this picture came out so terribly bad over here, but what you're looking at here is what we call the volcanic explosivity index. Last week, when we were looking at the shield volcanoes and some of those things, they rank down here kind of at like a 1 or a 2 in terms of how explosive that volcano is and how much ash. Basically, it's measured by how much ash, or how much tephra is the name for volcanic ash, it gets shot into the atmosphere. And usually the Hawaiian ones are more lava flows. So the flows stay on the ground and they don't produce these huge explosive ash columns or tephra columns. Now, if you get down to an 8, and this is a logarithmic scale here, this is a logarithmic scale. If you get down to an 8, we're talking about 10 to the 12th meters cubed, which is massive, or about 1,000 kilometers cubed, which would be what? 100 10 by 10 by 10, right? That's kind of what that's what a box would fill. 10 kilometers by 10 kilometers by 10 kilometers would make this much. That's how much it would fill. So imagine a box almost 6 miles wide, or 7 miles wide, 7 miles wide, 7 miles tall, and fill it all the way up with ash that got erupted out. And that's what some of the biggest volcanoes in Earth's history have done. And so this kind of also gives you a range of just how frequently or how often they happen. So the really huge cataclysmic style volcanoes on Earth, they happen about once every 10,000 years, if you average it out. It doesn't mean if we haven't had one in 10,000 years like we're due or anything. It just means on average, that's kind of when we hit that. So to give you a kind of put that in perspective, when we look at Mount St. Helens a little bit later on, Mount St. Helens is kind of right here in this neck of the woods, which is like 0.01 cubic kilometers of ash that erupted in 1980, or June 12th, 1980. Then on May 18th, 1980, it was about 1 kilometer cubed. but you can see it's nothing compared to like Yellowstone or Long Valley Caldera, which are some of these big circles down here. So we're going to talk about these volcanoes coming up now. And I just want to give you an idea of like, man, when we talk about this explosivity or how big it is, these are much more explosive than the Hawaiian volcanoes we were talking about last week. All right. And so this is another slide that just kind of explains it more about kind of the rate on Earth, how often it happens in general. That's what we're kind of looking at right there. All right. So let's look at those different flavors of volcanoes here and of these felsic volcanoes, and we'll get into it here and kind of probably get through this today and be good to go. So in terms of stratovolcanoes, if you look at all of these four images, you can chat it, you can say it. What are some things that these different volcanoes have in common? What are some common features here with these types of volcanoes that we're looking at? So this is Mount Hood, Mount Shasta, Mount Rainier, and I've never been to Mount Fuji. The first three pictures of mine, but I've never been to Mount Fuji. So what are some things that these mountains have in common here, these volcanoes? Similarities. You can chat it. You can say it. No answer. And I'm just talking about looks. When you're looking at these pictures, what are some common traits these things share? Or maybe how are they different from the basaltic ones we looked at last week? The shape of them. All right, that's a great one. Yeah, they're pointy. All right. I like that. That's good. That's one of them, or that's one of the things they have in common. What are some other things they have in common? Yeah, okay, maybe they look like they're kind of the same material. Yeah, they kind of look grayish in all of those for sure. Heck yeah. Any other thing you notice maybe at the tops of all of them? High altitude. How can we infer high altitude? What are we using to infer high altitude here? Yeah, the snow, you got it. So snow generally means it's higher in altitude, and that's where it's going to get. And I also notice there's some forests near the base, but no forests near the top for sure. So yeah, all these types of volcanoes and these types of features here, this is kind of what makes a stratovolcano, or another name for it is a composite volcano. This is what they are. Exactly what you said. They're tall and they're pointy. They look like they're made out of kind of this same grayish rock, which we'll see is called andesite in just a few minutes here. Yeah, and they generally have like glaciers and snow on top, which, believe it or not, adds to the hazards and the dangers of these types of volcanoes. And I'll show you why here in just a minute. So if we're talking about these composite volcanoes or stratovolcanoes, and I've switched the words because they both mean basically the same exact thing. If we were to kind of figure out what's the defining feature of these, well, they're usually tall. And when I say usually tall, we're usually like 5,000 feet plus. Oops, sorry. Oh, okay. Does somebody have a question? No, all right, no worries. They're generally tall. They're like 5,000 feet tall, usually. I mean, there's some that are a couple, 4,000 feet as well, but they're pointy and they generally can be very explosive. So they kind of have these periods of where they ooze out lava and it builds up these sticky, pointy points, and then that adds pressure to the vent and basically kind of seals stuff up. And if they have gas that builds up over time, it's not like the Hawaiian lavas where the gas can effuse out and escape easily. It builds up pressure. And the only way for that big pressure to release is if there's an explosion from those overlying rocks. So here's the big thing about these. These only form at subduction zones or near subduction zones, because you have to have the plate subducting to melt those quartz, feldspars, and mica minerals and hornblends and things like that that can come up and make these types of volcanoes. So the magma is what we call felsic. So it's felsic magma. It's kind of gray and sticky and viscous. It's not nearly as black. There's not as much iron. There's not as much magnesium in it compared to the Hawaiian volcanoes. And a lot of these volcanoes, this kind of flavor of felsic stuff is what we would call andesite. And technically speaking, andesite and felsic are their own two separate columns of composition or their magma types. But for us, if you say andesitic or felsic, it's all pretty much in the same ballpark. So it's fine for us for right now. Okay. And they make some of these different explosion types, which I'll show you later on, called Plinian and Palean. They're kind of explosive. And you can see the hazards down here are lahars, pyroclastic flows, toxic gases, and landslides. And don't worry, I have videos of these to show you exactly what they look like in just a few minutes. All right. So tall, they're about 5,000 feet. They have steep sides, whereas the shield volcanoes are very broad sloped and huge and wide, but not very pointy tall, like these ones. These are kind of like super big cone shaped like that. So there's Mount Shasta. It really last erupted a small leak quietly in like 1786, and out of Mount Shastina, which is this one over there. But if you were to take Mount Shasta and you were to cut it in half, like, so you can see this cone is much younger than the main cone over there. You'd kind of see these goofy alternating layers. And this is my poorly drawn alternating layers here with magma coming up through the surface, and you have kind of ash with sticky layers and ash and sticky layers and ash building up over time to make that pointy cone. And the reason it can make that pointy cone is because the lava is more viscous or more sticky, and it can retain its slope better than like the more runny lava that just oozes out in Hawaii. And so that's what I was telling you about there. So what are these pyroclastic flows look like? Well, last week we took a little bit, we took a look at in plate tectonics. I think we ran across Mount Sinabung once, but Mount Sinabung basically is down in Indonesia. And what's kind of cool about it is it's been constantly erupting the last 5, 6, well, actually 10 years now, the last decade, at least once or twice a year. And so here is kind of what a pyroclastic flow looks like coming down the mountain. And then this one is basically there was a lava dome here, which means it was lava bubbling up and pushing to the surface. And then it kind of crumbled and collapsed. It's still lava. It would be red hot if you could see it at night, and then started falling down the mountain like this, which is pretty intense. And so you can see these move many, many, many miles an hour. In some cases, they can move over 100 miles an hour and 200 miles an hour in some of the rare instances. But if you're standing underneath that, this is all still probably 1,100 degrees, 1,200 degrees, something like that. It's just going to instantly vaporize anything in its path as it moves down the mountain. So being far away from it, good. Video from far away, good. Being right here, not good. And there are volcanologists in history that have gotten too close to a mountain and had a pyroclastic flow wipe them out. So yeah, if you're standing really close to it, sometimes they can get up to about 1,800 degrees. But the further away it gets from its source, it cools down over time. And oh, by the way, the pyroclastic flows, these were the things that were from Mount Vesuvius in Italy. This is what caused the burying of Pompeii and Herculaneum, all these little ancient cities that are around Naples, Italy today. And these pyroclastic flows came through and basically buried everybody in that hot ash. And within that hot ash, the people that got buried there, their bodies cooked and burned and decomposed pretty quickly, leaving voids and holes of their bodies, like molds basically of their body within the lava flows. And so what archaeologists and other folks have done once they were excavating these sites, they noticed the voids, and so they started pouring in like plaster and other stuff to basically make a cast of what the people were doing when they got covered in lava. So I mean, it was pretty instantaneous, pretty bad. They actually find a weird, and this is kind of gross, but it's an interesting tidbit. They find obsidian around some of these people. And now what they've realized is it was people's brains basically getting cooked and exploding and interacting with the ash from the pyroclastic flow, basically creating a volcanic glass from exploded people. which is terrifying to think about. But this is why we have to learn how to understand these volcanoes so we can evacuate folks so it doesn't happen to us. So Vesuvius, by the way, it would have been before 79 AD, it would have been much more pointy like that, and then pretty much lost all of that in the eruption in 79 AD, which is just really intense to think about. And there's still multiple millions of people that live around here today. So if it ever erupted that largely again, it could be some catastrophic things for a very large city in Italy. So those are pyroclastic flows. The second type are called lahars. And this is from, oh man, I can't remember which geology agency. I can't remember which one, but it's a pretty slick thing. Let me share my sound here.
Floods of water mixed with volcanic debris. These floods are called lahars. Lahars are more destructive than a normal flood because they contain large amounts of rock, ash, and mud and debris. Boulders swept along by the lahar can sometimes be the size of a car.
So when we're talking about lahars here, these are that mud ash like they were talking about here, but it's like liquid concrete. That's the best way I can describe it, is kind of just like liquid concrete. And it comes from melting and mixing with the snow, or if there's a rainfall or things like that.
Quickly and flow down the volcano into the surrounding valleys, often at high speeds. Several lahars often occur in quick succession. Lahars are a major cause of death in volcanic eruptions. They can travel great distances, many kilometers or even many tens of kilometers, so communities far from the volcano can still be in great danger. There are many causes of lahars. A very common cause is if there is heavy rain. An eruption can cover the sides of a volcano with loose rocks and ash. Vegetation and soil, which normally absorb the rain and prevents floods, can be destroyed by the eruption, adding to the problem. When it rains heavily, rock, ash, and debris are easily swept into the water, forming lahars. The rocks and debris give the lahar extra destructive energy, and often the flows move much faster than someone can run. Some volcanoes are covered in glaciers and ice.
And so for the United States, big volcanoes, the composite volcanoes, a lot of them you saw earlier have the big glaciers and stuff like that on them. If there's a steam vent that erupts underneath here, or maybe magma gets close to the surface and even steam starts erupting, it can melt the snow, which causes a rapid runoff, and then it will erode some of the looser sediments and looser rock that are on the top of the mountain and bring it down as a lahar as well. Now, if it erupts and all the snow melts pretty quickly, that's even worse. And there is also, I got to think, there's a place in Colombia, I think it was Nevada del Ruiz, that had a volcano that had a glacier. A volcano erupted, melted the glacier, and I think that one ended up killing close to 15 or 20,000 people. I gotta double check, but it sent a lahar down a valley to a place where people were sleeping at night. It was late 70s or early 80s. And so lahars can be super deadly, and that's why we now can have warning systems and understand when things like that could happen and have sirens and alarms to get folks out. So you'll see kind of how this looks here.
Of hot rocks can melt the ice or snow rapidly to form bursts of huge volumes of water that form lahars. Lahars can occur at any time during a volcanic eruption, but they can also happen many years afterwards. Fortunately, there can be warnings given about lahars. If heavy rain is forecast, then the chances of a lahar increases. For those places threatened, evacuation is the only option. If there is not enough time to evacuate, then people can protect themselves by immediately leaving valleys and going to higher ground. Hiding in buildings is not safe, as large lahars can destroy buildings or flow into them.
So that's the big thing, is you got to run uphill, get out of the low-lying areas, and that's how you get out of lahars. So lahars are these volcanic mud flows. That's another hazard that these composite volcanoes can have. And then the third one are these tephra, or what we call ashfall. And this is basically just microscopic glass and rock shards, these really small particulate matter that get erupted out. And then when they start falling down out of the atmosphere, it basically makes these huge piles of dust. So you're going to see somebody driving through it here.
Se le recomienda a la ciudadanía mantener las siguientes recomendaciones. Por favor.
Oh, so the name, and somebody's asking in the chat, the name of the first volcano or the hazard, the lahar, is that the one you're asking about? Lahar? Yeah, I think. And so, yeah, so those are the lahars. This is what we call these tephra or ash flows. Oh, the pyroclastic flow, maybe, is that was the first one you were talking about, the pyroclastic flows? Yeah. All right. And so these are the ash falls. So this is away from the pyroclastic flow. It's not like super hot. It's from ash that blew up in the atmosphere and then starts settling down. And what's important to see here is, I mean, imagine these microscopic shards of rock getting into your air filter systems, getting into all the mechanical moving parts. It's harder than steel, so it will scratch steel and things like that. This is why when there's a volcanic eruption, you can't fly through those areas, because the volcanic ash can really impact the way jets fly and stuff like that as well. So this is volcanic ash or tephra, and sometimes you'll see, if you're close enough, like in Cinnabung and some of those places, if you're within a few miles of the volcano, sometimes they might end up with 3 or 4 feet of ash on their roofs. And remember, it's not snow, it's dense rock. And that ash buildup can literally collapse houses and things like that. So these are some of the hazards that these composite volcanoes pose. Tephra or ashfall, pyroclastic flows, if you're really close, that comes streaming down the mountain, versus lahars, which are kind of the mud flows that go there. And so what we looked at today, we kind of saw Mount Shasta and Mount Lassen a little bit here, but what's kind of interesting is we have this whole range, the Cascade range of volcanoes right here. They're nearly all composite volcanoes, almost every single one of them. And so take a look here. This is kind of the eruptive history of all the different Cascade eruptions or volcanoes in the past 4,000 years. So I want you guys to think about which volcano out of this list, and you know, they need to make a new one of these that have the actual indigenous names for these, but they don't have that one yet. But my question here is, which volcano would you least want to live by, or would you be most concerned about if you lived near it in the Cascades here, based on this chart? You can see it starts from 4,000 years and goes all the way to present time. What do you think? And the red line means it's erupted within anything on the right side of the red line. All right, so somebody says Mount St. Helens. Why St. Helens? What's concerning about that to you? A lot of folks agree with St. Helens. What's concerning about that data that makes you go, ooh? Oh, it has the most eruptions. Okay. So lots of eruptions, seems like it's pretty frequent. All right, so if it's done it in the past, maybe there's a history that it could go again pretty quickly. Yeah, it seems super active. So is there any other argument to be made that maybe one of these other volcanoes might be more concerning or disruptive or destructive? Could you make an argument another way, kind of a, like, how about Jefferson? Like, if I'm taking a look at Jefferson here, it hasn't erupted in the last 4,000 years. So what do y'all think? Is that something like, okay, it's totally fine, or? That's a great, so somebody says maybe one that hasn't erupted frequently, maybe it's just kind of saving up for a big eruption. And that is definitely a concern that folks have to think about sometimes and study it. And so the only way we can know is by putting sensors and monitoring and figuring out what types of stuff are coming out of the volcano to help us understand if it's going to erupt big. But most people say Mount St. Helens, and I need a quick drink here. Yep. Most people say Mount St. Helens, and I would probably tend to agree with you for the most part about Mount St. Helens. Here's what it looked like prior to May 18th, 1980. And then it started getting this big bulge on it. And as the bulge on the mountain increased, it actually weakened some of the layers of the rock beneath Mount St. Helens and caused a huge landslide. And as the mountain slid off, so that's what you're seeing here in this one picture, is the landslide starting to happen and going out. It kind of uncorked the whole magma chamber and caused this huge massive eruption. I think the landslide caused a magnitude 5 0.3 earthquake or something like that. It was a huge landslide. I still think it's one of the biggest in recorded history, like people have witnessed in written times. And what's kind of interesting about it is it lost several thousand feet of its cone. This is kind of what it looked like when I was last there 10 years ago or something like that after it erupted. And so I'm going to mute these guys, but I just want to show you here kind of, they were able to take, there's 3 still pictures of the eruption from the side. And what they've done here is they've taken these and they've kind of started to animate it to kind of show you what it would have looked like. So it was bulging, bulging, bulging. Here it goes. And then they kind of morphed it and animated it to show what the landslide would have done, how it slid out. And then as it slid out, it uncorked everything. And he's a geologist too. But let's see, there it goes. It uncorked everything and allowed the eruption to really go crazy. And what was different about Mount St. Helens here is that, you know, prior to 1980, most everybody still thought volcanoes just shot straight up. And they just shot straight up and there was not ever going to be a problem. But this one had the landslide that poured out. And some of the chunks of the mountain, the layers, the strata of the volcano here, they flowed almost 5 miles downstream in that landslide. So imagine chunks of this mountain literally running downhill for 5 miles. And that's what we can still see today, which is pretty impressive. So if you fly over Mount St. Helens, like flying from anywhere in the Bay Area or Sacramento to Seattle is just awesome. I mean, you fly right over all the Cascades, you can see the volcanoes most of the time. And so get a window seat because it's pretty great. But we have evidence of big, huge landslides in California too. Mount Shasta, if you drive up out past Weed and stuff and past Black Butte, which is a cinder cone, you'll notice these what we call hummocky landscapes. And it turns out all of these funny looking piles of debris and stuff, that's from pieces of an old Mount Shasta from 200,000 years ago that basically had such a huge landslide, all of it flowed out this way. So everything you're seeing here are landslide debris from what used to be the previous Mount Shasta about 200,000 years ago. So it basically completely destroyed itself. And in the last couple 100,000 years, Mount Shasta has built its way back up through multiple eruptions over time. And there's Mount Shastina right here. And by the way, this type of data that you're looking at is called LIDAR, where they use laser beams. They fly over it with laser beams and can basically remove vegetation and stuff like that to show the ground below. Was there a movie about Mount Shasta or Mount St. Helens? St. Helens. There's probably been a few. I think maybe like the most popular science fiction movie about Mount St. Helens, or not Mount St. Helens, but is Dante's Peak with like Pierce Brosnan and stuff. That's a pretty big one. But there's been lots of documentaries about Mount St. Helens. And it's really cool. If you go to Mount St. Helens, the visitor center, you like watch this documentary about it, and it's kind of big surround sound and like super not interactive, but immersive. And then what's really awesome at the end is like the whole curtains go, and as the curtains open, you're sitting there viewing the actual volcano after you've watched all the destruction happen on film. It's pretty cool. So yeah, so Dante's Peak, Dante's Peak, I wouldn't be surprised if you saw it in like a 9th grader science class or something like that, or a documentary on Mount St. Helens for sure. Dante's Peak is a really interesting one, and it's probably the best version of a volcano movie in Hollywood. That's science fiction. It's kind of almost somewhat accurate in parts, which is pretty great. So the last one that I want to show you then, these are plug domes. And so the plug domes are literally domes of lava that ooze out of the ground and plug up the volcano's vent. It's a dome that plugs it up. That's why it's called a plug dome. All right. And so with these, we get these tectonic settings, convergent boundaries, near subduction zones again. They're felsic or rhyolitic lava. They can still sometimes have a few little explosive eruptions here for the most part. But for the most part, it's usually just kind of oozes out. So it's less gaseous, it's effusive. Effusive means to just kind of ooze out of the ground without having a big, it's the opposite of explosive. All right, that's what effusive means. But you can get small ones like this in the middle of Mount St. Helens, the small dome that was there, or you can get really big ones that are what Mount Lassen is, and some of the plug domes over in the Eastern Sierras and the Mono craters that y'all took a look at the beginning of class. And they can all still produce the same hazards, just like the composite volcanoes do. And so here's kind of a neat plug dome being built over time from 2004 to 2008 in Mount St. Helens. So after the big eruption blew, then there was another eruptive period starting in 2004. And you can just see all this big dome of lava being squeezed up. And it's lava, all right? It looks like solid rock. And then when it cools, it becomes solid rock. But it's lava. It's a flow of really sticky lava, as opposed to the really runny lava that we saw in Hawaii that just flows out and makes those big lava flows. These ones just pile up and they dome up and they make bulges. And this is what eventually builds the volcanoes back up to being pointy. So until another gaseous magma comes in and then blows it all apart. So that's kind of how these go. Isn't that cool? Just see these big fins of dome just squeeze out of the ground. I just think that's so cool. And they have good video of it for most of the year. And it made these really big ones. And so if you look at it from air with the LiDAR, this is what those domes look like over time. So you can see, you'll see in the back here, after they scan it, you can see how the rock and the dome started adding to it and building here. And then what was kind of really crazy about this is it provided a kind of a cold valley right between the mountain, the rim, and the dome. And there's a glacier there now, which is pretty cool. So it's called Crater Glacier. But here's the dome from 1980 to 86, and then another dome building event in 2008. And so far it's been quiet. We monitor earthquakes there, we monitor gases, and there's nothing to be worried about at this time, which is good. And so those Mono craters you guys saw and flew around earlier, if you go over Yosemite 120, you drop down into the valley right on the other side, and that's where all the Mono craters are, next to Mono Lake. And these are all plug domes. The largest plug dome in the world is Mount Lassen. And here's what it looked like from Redding, or Anderson, basically, near Redding, back in 1915. And I think somebody needs to make a disaster movie about Mount Lassen erupting back in 1914. I can just see like somebody trying to hand crank the car, trying to get it to go and trying to outrun these little like Model T cars with pyroclastic flows coming at them or something. I think that would be pretty fun. So maybe somebody should make that on TikTok or something. Okay, so last one here, calderas. Whew. All right, so calderas are these huge, these are what we know as, a lot of folks know as super volcanoes in the media, but these are huge volcanoes that after they erupt so much volume, and I got to move my face over here so you guys can see this. They erupt basically for a long period of time, and they kind of expend all the magma that's underneath them. The whole magma chamber gets used up. And when that magma goes away, it just leaves a big void under the ground. And the rocks on top aren't supported anymore from the magma that was pushing out. So those rocks collapse in on themselves. And as those rocks collapse in on themselves, it makes big depressions, and they usually fill up with lakes and things like that, if they're kind of small enough. So these also happen at convergent boundaries. They're felsic magmas. They have the long-lived Planaean biggest eruptive types that we can think of. That's the largest VEIs there, Volcanic Explosivity Index. And they have all the hazards in the book, all right, that you can think of. That's what it is. And this is Crater Lake. I was also there this April, but I didn't put one of those pictures in. But to give you a sense of scale here, Crater Lake, the crater is about 5 miles wide. That boat that you see right out there is this boat right here. It holds like 50 people. And that's, they give tours. It's a national park, and you can go take a boat out on the middle of Crater Lake just to see amazingly how big it is. All right, so I made a little magma chamber here. So I want you to pretend that this balloon is a magma chamber. My son was helping me out here, and we're gonna bury this magma chamber with flour. And we've buried it with flour just like that. And now I'm gonna show you what happens. We're gonna filled up with air, pretend like magma's coming up to the surface. So kind of looking like, well, you'll see here. I'll unmute it and just let myself talk.
Really hot melted rock underneath the surface of the Earth. What happens when it starts bubbling to the surface? What will it do to the crust, this hard rocky area? So I'm going to start pumping in some air to represent that magma. And remember, when enough cracks happen on the surface of the Earth, some of that magma will erupt as lava and make a big volcano. So here's what that might look like.
I will say this was an audience of first graders I made this video for, but the model is good.
What do you guys notice and wonder as I pump in the magma here? Keep pumping it in here. So in real life, this would represent an area about the size of Turlock. So imagine taking all of Turlock and putting it on something about this size here. So all that magma is coming up from the surface. There's probably big eruptions happening here. Lots of ash and steam and lava being shot.
And the balloon wasn't holding air very well, so it wouldn't be like a heaving, breathing thing, but you get the idea. But here's the thing that's
out everywhere.
What happens after.
But then eventually the magma gets shut off. No more magma can come in there, and it all erupts. And after it all erupts, there's just a big hole. And so all the crust that was on top that got broken up sinks back down in, and this hole is called a caldera.
So there you go. That's how calderas form. If you want to make it with flour, that's how you do it. But what's kind of also awesome is they're in Crater Lake. They've had a few little eruptions since the big caldera collapsed about 7,000 years ago. And we have little cinder cones called Wizard Island. There's a few lava domes under the lake there that you can go check out. But what's kind of interesting is we can reconstruct the size of how big Mount Mazama was, which was the name of the mountain before Crater Lake 7,000 years ago. We can basically trace up these layers of and the angles of these rocks on the side, on the craters of these walls, right, that you can see like right here, and we can trace it out to see, ooh, it was a big, huge stratovolcano at one point too. And so one of the things we'll talk about on Thursday when we come back, we're going to look at the hazards to California. And one of them is Long Valley Caldera, which is a huge giant dome, but Crater Lake is like 5 miles wide. Long Valley Caldera is 10.5 by 19.5 miles wide. And it last erupted about 760,000 years ago and was literally 600 times bigger than that Mount St. Helens eruption. So we're going to figure out if that's a problem, if that's something we should worry about, and how will we know if it's something we need to worry about. All right, and that's what we're going to do on Thursday when we come back. We'll get into some more California ideas about how to stay safe and what we need to worry about. We'll look at Yellowstone, and then we'll go from there. So this is kind of the background information. Thursday is the doing, and we'll have some good time. So other than that, that's pretty much what we got for today. We'll take a look at some of this just really fast when we start on Thursday to refresh our memory, and we'll move on from there. So if you don't have any questions or anything, that's all I got for today. And I hope you have a good rest of your Tuesday, and I'll see you on Thursday.